Okay, it's time for calculations with magnetism. Actually, we're only going to do one calculation in this video because it's the one that is kind of icky, and it's like the most simple thing. It's the one, well, it's not an easy equation. It's the one that tells us what kind of magnetic field we have around that wire. Okay, so let's say we have this wire with a current moving to the right. Go ahead and use your right hand rule. Point your thumb in the direction of the current, so it should be pointing to the right, and then pretend like you're grabbing that wire. And you'll see that your fingers curl around, and you should be able to see that if you curl around far enough, your tops of your fingernails. And you should see the palm of your hand and the tops of your fingernails. So that tells us that on the top of the wire, we have our magnetic field coming out of the paper, because that's where, if you look at your fingers, you're seeing like the tips of your fingers there. That means it's coming out. And then if you continue down and continue around, you'll see that your fingers are pointing down at that point. Go ahead and twist your hand all the way over, curl it, curl it, curl it, and you'll see that your fingers are pointing down. You should actually be looking at the back of your hand right now. So our magnetic field is coming out of the screen here, and it's going into the screen here. Remember, the dots represent the tips of the arrows, and the X's represent like the tail feathers on the arrow. So that's just, we have a wire, it has a current going through it, it has a magnetic field going around it. Now here's how we would calculate how strong that magnetic field is. Now aren't you so glad you asked? B, okay, this is the symbol for our magnetic field. I don't know why it's a B, but it is. Because it really doesn't make any sense, because the unit for the magnetic field is capital T, which stands for Tesla. Just like the rock band. Dun, 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 dun. Okay, so the unit is a Tesla. Most magnetic fields are very, very, very small, and they're not on the order of a Tesla. I think an MRI machine might have 2 Tesla. And if you've ever been in an MRI machine, they have a super strong magnetic field. Anyways, mu naught is a constant. It's the permittivity. Let's write out that word. Permittivity. Basically, how well it permits of a vacuum. So how well a vacuum allows a magnetic field to go through it. It has a number, 4 pi times 10 to the minus 7. It has units too, but we don't care about those. I, V equals IR, remember that? There's our current again. And R here is your distance from the wire. So we can see from the equation that as you get further and further away from your wire, you're not going to have as large of a magnetic field. As you have a larger current, you're going to have a greater magnetic field. So our magnetic field is basically going to depend on our current and how far away we are. And so there's our basic, that's one of our equations. This is the magnetic field around a wire. So let's write that down. Magnetic field around a long wire. Okay, and that's how we would calculate it. Good? Alright, so let's put that to use in an example. So here's a problem from your pretest. How far from the center of a wire carrying 2 amps of current does the magnetic field that results from the current have a magnitude of 4 times 10 to the minus 4 Teslas? So see how the Tesla number is really small? So we're going to use our equation, B equals mu naught I over 2 pi r. Okay, so we know our B. B is 4 times 10 to the minus 4, because that's our magnetic field. We know our current. Our current is 2 amps. Generally, we're going to have a little bit larger currents. Instead of having milliamps, we're going to have like amps. And we want to find our distance. So 4 times 10 to the minus 4 is equal to mu naught, remember that's a constant, 4 pi times 10 to the minus 7 times our current, 2, divided by 2 pi, and then we're solving for r. Okay, so let's see if we can solve this. What do we get for r? Remember, be careful, r's on the bottom. Be careful. That's 0.001, and remember, SI units, that's in meters, so that would make our answer 1 millimeter. See, that wasn't that hard? It looks ugly, but it's not that hard. Let's try one more. So here we go, number 40 from the pretest, the next one. Okay, let's write down our equation real quick, just so we remember it. B equals mu naught I over 2 pi r. Okay, so a very long wire generates a magnetic field. See how small that is? 0.005 times 10 to the minus 4 is equal to 4 pi times 10 to the minus 7. That's our mu naught. Remember, that's a constant. You're going to want to put that on your equation sheet. Times I, that's what we're looking for, over 2 pi times, okay, what is at a distance of 3 millimeters? So make sure you convert that to meters. Now here's one little thing you can do to make your life easier. See, you have here 4 pi and 2 pi. Guess what? That's going to cancel and give you 2. Okay, just saying. But it's in there to make the equation a little bit more conceptually correct. 2 pi r being the circumference of that circle around the wire. Okay, because that actually does matter in the grand scheme of things as you get bigger and older and smarter, which we're not there yet. So we have all of our things. We just need to solve for I, and we get I equals 0.0075 amps, which is 7.5 milliamps. Now this answer makes sense. If you compare this with what we had in 39, 39 was 1,000 times bigger than this, and our current was 2 amps in 39. So this makes sense that with the hugely smaller magnetic field that we would have a hugely smaller current. Okay, so you can kind of use those ideas. Does my answer make sense? So that's it. This is just for the current around the wire. In the next video, we're going to explore the 2 equations that you were given in the first video. We're going to explore the force on a wire and the force on a charge. And that's it for today. See you tomorrow. Bye-bye.